Welcome to the last day of the conference. Thanks for all of you who have shaken off the food and wine hangover from last night to this morning. Today we'll have a session on streaming and analytics frameworks. And our first speaker, we're happy to have Michael Franklin. He's a professor of computer science at UC Berkeley. He's the director of the Algorithms, Machines, and People Lab, and the founder of Treviso, which last week was bought by Cisco. So congratulations.
All right, thank you.
And his talk will be on continuous analytics.
All right, well, thanks. I don't know, I know you guys have had a wide range of talks on a wide range of different topics. I don't know how much database stuff you've heard so far, but how many people in the audience speak SQL? Oh, okay, so good. All right, I'm going to be in trouble, actually. All right, okay, so why don't we just jump into it? So yeah, continuous analytics. So here's the overview of the talk. The argument I want to make to you, and maybe you don't have that much invested in this, so maybe it'll be okay, is that sort of the traditional way we think about doing analytics, whether it's a database or a NoSQL, Hadoop-based system or whatever. We like to take a bunch of data, we store it, and then we turn around and we pull it back out and we try to analyze it. Okay. And if you at all think like an engineer, you have to realize that seems kind of inherently wrong, right? At least for certain use cases. And so, the argument I want to make is if you think about sort of big data problems in general, you've got this streaming amount of data just constantly coming in, and that's not what you want to do. What you want to do is you want to be able to process that data as much as possible as it's arriving. Okay, because, and we'll go into this, but obviously writing it out to disk and bringing it back is expensive. Going through even if you're not writing it to disk, going just through that whole software stack all the way to store the data and then bring it back is expensive. And so, to the extent you're able to do it, as data's coming in, you'd like to process it. Okay, and so that led to a class of systems called streaming systems, but they're not exactly the right answer either. And my argument that I want to make to you is what you really need is a system. Hey, Ron. You want to build a system that combines kind of the best, I'd like to say the best, of a traditional store-first system plus a streaming system. And I kind of use the clunky term stream relational for that. Okay? And so that's really the technical part of the talk. And then, this is kind of an interesting checkpoint for me, as was just mentioned. There was a bunch of research. There was a company. The company just got bought. So, along the way, I'll sort of maybe give some insights or reflections on sort of what this process has been like and what I learned along the way, both technically and maybe a little bit about why it's a good thing I have a tenured faculty job compared to why I'm not in business, I guess I should say. All right, so that's it. So let's start. So, around the turn of the century, a lot of us got excited about the Internet of Things. Everything was going to be connected. Everything was going to be collecting data, pumping that data out. And how were you going to make sense of this data? You certainly weren't going to stick all that data into Oracle and then try to run queries on it. That didn't seem right. So there were a bunch of people around the research community, especially the database research community, saying, how do we build technology to do the kinds of things we like to do with data, but do it in this world where everything's connected, data is constantly on the move. Okay? So that was, 10 years ago. At Berkeley, we spun up a bunch of kind of a series of research projects that were aimed at that basic idea. We had a system called Telegraph CQ, which was one of the early database streaming systems. I'll talk a little bit about that. It's actually the sort of the foundational work that led to the system I am going to talk about. We built a system called TinyDB where there was a burst of energy here at Berkeley on these little, I'm going like this because these little wireless sensor modes that you could build ad hoc networks of, and they would be able to sense environmental readings and collect them and route them to this ad hoc network. So we did this work on TinyDB where we basically made SQL the programming interface for wireless sensor networks, and that was a very popular system that we built. And then a little after that, we built this thing called Hi-Fi, which this is a picture of, which basically combine these things. So we use TinyDB out on the edge of the network to manage collection of data from physical devices. And then we used a streaming engine, Telegraph CQ, to basically aggregate data and build a hierarchy. So you'd have a bunch of edge devices. You'd have a bunch of things out measuring, sensors and so on. Those would connect to sort of gateway devices, and then there'd be a hierarchy of gateway devices and servers up until you got to maybe headquarters where you had your big data warehouse. And our view was you'd use SQL out here because we did have a tiny DB. You'd use SQL in the middle here because that's what we could do with Telegraph CPU. And then you'd have your traditional tools and BI tools and stuff up here. Okay. And what this is a picture of, it's we built this thing called the loudmouth sensor, and we demonstrated it at the LDB conference. So everyone that came in got an RFID tag that they wore on a lanyard. And then we had around the conference room, we had stations set up where we had an RFID reader and then a little network of wireless sensor modes that had microphones on them. And at each station would measure the total noise volume and would count the number of people in the neighborhood, and then would divide. And we built a SQL view on top of that that basically was loudmouth sensor. And what it would do is it would give you the ratio of noise to people, and then we'd just run a SQL query over that to figure out where are the loudest people in the room. And then we had loud people kind of go from one place to another and make a lot of noise, and we showed how we could track them in real time. But the important part of that was you didn't have to write any imperative code. It was all done with views and queries, which was something that a lot of people working on sensors at the time, thought hadn't really thought you could do it, or really hadn't thought about doing it. Okay, so that's sort of the genesis. That's kind of the sort of the research milieu, if you would, of a lot of the streaming database work that was done, sort of 10, 12 years ago. So, the story I have, so a couple of years after we wrapped up the Telegraph CQ project, one of my PhD students was graduating. We got approached by some investors who were interested in real time. Michael Stonebreaker, who had a project at MIT that he did with some folks at Brown, had spun out this thing called Streambase, and people, as investors tend to do, say, hey, we should do that. And so one thing led to another, and we ended up starting this company called Treviso. And we ended up in kind of a very different place than the picture I just showed you. And we ended up there because we went out into the world. When we started, our view was we were going to go out and be the kind of the analytics for the Internet of Things. But that's sort of not the way it turned out. At least it's not the way it's turned out yet. And so, we ended up kind of getting involved in sort of the big data analytics world. And as was mentioned in the introduction, last week the company was acquired by Cisco, which is actually one of our first customers. Another early customer was UPS, the package delivery guys, and so it was people like that were interested in the technology, but none of these people were deploying those little sensor devices, right? It was all sort of big stuff on the network. Okay, so this is kind of the experience I'm going to be talking about. So here's a little background. Maybe some of you already know this, but think about a stream as a sequence of records that's unbounded, right? Just keeps coming in. All right, we all know what a table is. A table is a set of records, right? So got rows and columns. And we all know how to get information out of tables. We write SQL. Okay, so SQL queries apply to tables. And then, so the only thing you need to do to bridge from this world of continuously arriving data to the old world that we all knew and understood, which was the world of tables, is use this thing called a window operator, right? Which is just a single query operator that converts this continuous stream into a sequence of tables. Okay? So here's a bunch of records coming in on a stream. Here's our window operator that we'll talk about in a little bit. And what pops out of that is a table. Okay? So every time the window operator spits something out, what it spits out is a table. Since it's a table, we already know how to use it. We write SQL on it. Okay? So it's a really nice kind of, it's a nice simple way of being able to move 30 years of data analysis technology into this new world of moving data, okay? And, this wasn't just our idea. I mentioned the MIT Brown guys. A lot of the really good work on understanding exactly what these operators should do and what they mean was done by Jennifer Whittam and her group at Stanford. And actually, I have a slide on this. It was a big topic in academia, Okay? So every time the window operator, every time that window closes, you can conceptually think of a new table coming out. Okay? And then, you know, our particular semantics were that, you know, the results, every time you produce a new result, it sort of gets appended to what you had already. There's other ways to think about it, but that one turns out to be pretty simple. Okay, so here's an example. Let's say that you were doing an advertising thing, and here's your query. So every 3 seconds, give me the revenue for pay-per-click ads per advertiser over the last 5 seconds. Okay? And the way you do that in a system like the one we built is you write a SQL query. Instead of having a table in the front clause, you put a stream there. Okay, so this is an impression stream. And what I'm doing is I'm looking at this impression stream. I'm only interested in ad impressions that are of this type CPM. That's advertising lingo for pay-per-click. It's cost per 1,000 impressions, CPM. And, you know, I want to group those by the advertiser, and for each one I want to output the advertiser and, you know, this metric that tells me how much money I made from it. Okay? So, so that looks almost exactly like an SQL query, except that this thing's not a table, it's a stream. And so in order to turn it into something that we can understand, we use this window clause, which is this thing here. And the window clause just follows what we're saying here. It's got 2 pieces. It says visible 5 seconds. So it says, I want to look at, when I produce my table, I want 5 seconds of data, right? So take the last 5 seconds of data, and do that every 3 seconds. That's what advanced 3 seconds means. Okay? So what this thing is going to do is, you know, these impressions are just streaming in. After 5 seconds, I'm going to get the first answer, right? It's going to spit out, this is conceptually, it's going to spit out that 5 seconds worth of data as a table, and then I'm going to run everything else, except for this is SQL. So I'm going to run this. I'm going to pull out the things like CPM impressions. I'm going to sort them and, you know, or hash them and group them by advertiser, and I'm going to calculate this stuff and spit it out, just the way you would in a SQL query. Now, of course, if you did it that way, it would be horrendously slow, right? So the secret sauce and the magic and the fun part of all this stuff is how do I give you those semantics, but don't really wait 5 minutes and then produce a table and then run the query, right? What I want to do is every time a record comes in, I want to incrementally update the answer so that when that 5-second window boundary hits, you know, boom, you've got the answer right then and there. You don't have to do anything else. And that's how you get low latency. Okay, so 5 seconds, I get an answer. 3 seconds go by, I get an answer, another answer based on the previous 5 seconds. So you'll notice in this particular case, there's some overlap, right? Every answer contains 2 seconds from the previous answer. That's okay. All right? So that's the semantics. That's what streaming SQL looks like. Okay? And you can see it's not a huge intellectual jump to go from a traditional database system to that. Okay, so this, as I mentioned, was a really hot research topic for databases. You know, it goes back much earlier than 2000. You know, there were this thing called active databases, these event condition action rules, you know, pub sub and various types of triggers and so on, and data broadcasts. But it's really interesting. If you do this really unscientific thing, which is you go to the DBLP database and you search for papers that have the word stream in the title, what you find, and I just did a piece of my DLP and data engineering, there were about 10 from the beginning of time up to 2001, and then since then there's been about 300. So, you know, and it's sort of peaked. I didn't really look, but it's kind of on the way, it's way on the way down now. Okay, but the real height of this stuff was, you know, sort of around 2002, 2003, so on. It's when the research community got really excited about it. Okay, and what was really fun about this is, you know, having participated in the academic side of this, is it was one of those rare times, at least in the database field, where a bunch of groups around the world were all building systems and were all sort of competing, you know, on the same playing field. And so all these different groups and many more built streaming systems, and you would go to a conference and people would, you know, be debating the merits of these various things. It was just like at the dawn of the relational database era when you had the System R people and the Ingress guys here and other people around the world, you know, sort of debating about what are the right implementation techniques for this new type of system. So it's really an exciting time. And, you know, there were a lot of startups that came out of this. And so, well, Gigascope is still at AT&T. Our stuff led to this company called Treviso. This project led to Stream-based company. This project led to a company called Correlate that got bought by Sybase, that got bought by SAP. The Wisconsin project, a bunch of those guys ended up getting hired by Microsoft. Microsoft now has a system called Stream Insight. So there's sort of direct and indirect lineage from all this academic work into things that have been sort of coming out as products from both small companies and big companies. So it's really very fun place to be. Okay, but so now let's talk about let's start rolling the clock forward. So, here's kind of the pitch that people were making then and are still making, okay? And the pitch is, the next big thing is going to be real time, right? If you pick up any sort of trade magazine, or the reason we're having this conference, right? We used to all do machine learning, but we didn't do streaming machine learning, but now, we want to do streaming machine learning. Why? Because there's tons of data, and we want our answers quickly, right? We don't want to wait 2 days till we get the answers. So everybody knows that, what you really want is real time, right? And this is a total, I'm going to show you a bunch of graphs. I apologize in advance that don't have numbers on the axes, which means you shouldn't trust them. They're for marketing people. But they're there to kind of make a point. They're not really graphs. But if you go from sort of months, days, hours, minutes, seconds, to sub-second, you could argue that if you're trying to make decisions, there's much more value in having data when you need to make that decision than later. Okay, so if you have to make a decision now, getting the answer to your query tomorrow doesn't help you. That's kind of all this is saying, right? So, and it's such an obvious thing that people have been saying for years, this is where the business intelligence world is going to go. It's going to go to real time. And if you search on the web today, I can almost guarantee you will find a blog post or a product announcement or something that says exactly that in it that was published today or yesterday. And I haven't checked, but they come out every day. Okay, the thing is, the traditional stuff, the batch stuff, where you save up a bunch of data and then you process it, right? That forces you to live out in this part of the curve, right? Days, if you're lucky, maybe hours, okay? But you're not getting instantaneous answers, right? And the argument is that you want to be out here. You want to be able to get the data, the answers right away, so you can make your decisions. All right? So I'll show you a different picture of this in a second. All right. So here's kind of lesson number 1 that I've been learning the hard way. So, here we are, today. We've got some existing technologies that people are using. We've got existing applications that people are using them for. Okay. Now, here's us, right? We're bright people. We're researchers. We walk around in white lab coats. We come up with crazy new ideas. Okay. So how do we impact the world? All right. Because the world is here. That's not where we are, right? Because we're doing cool stuff looking forward. So what can you do? And it turns out you have these 3 options at a high level. I call this an MBA on a slide, right? And I believe that there are, anyway, there's a lot of classes where at the end of it, this is actually what they're talking about. So you can move, okay. So you can have existing technologies that you're using for new applications, right? So here's this technology that's been out there, and I figured out something new I can use it for, right? This one says, hey, there are things that people need to do, and I've got a new way of doing it, right? That's the new technology, existing application. Or you could go here and say, hey, there are these new things that people should be doing, and I've got this brand new shiny box that's going to let people do it, okay? And here's what I learned, is that this way you can do, all right? So, you've got this database engine, and hey, guess what? Or you've got some machine learning engine. Guess what? It actually works for recommending movies to people. Who knew that, right? So that works, okay? Or you can go this way, and you can say, I've got a better way to do something that people already want to do, okay? But what's really, really hard, and what people like us with white lab coats like to do, is we like to go this way, right? We like to say, hey, here's this great new thing you can do. You can have sensors on everything, and here's this brand new technology for doing it, okay? And it just turns out, that there's resistance going this way, there's resistance going this way, and the resistance is kind of squared going this way, right? Because you're trying to get people to do something they're not usually doing, and you're trying to get them to do it with something they don't even understand how it works. Okay? So, you know, when we were thinking about building the Internet of Things, we were really going this way. And it's just hard to do. It's not that it's impossible, it just takes a really long time. And, you know, if you're a venture-backed startup company, there's a clock ticking from the time you close that first round of funding, right? So just something to keep in mind, okay? If you're a PhD student, there's a clock ticking, right? So anyway, so that's kind of, we'll come back to that. But, you know, kind of what happened to Treviso, just to sort of cut to the chase, is we're currently going this way, all right? You know, Cisco does a lot of network analysis. They have a bunch of ways they're doing it now. The engine we built, we think, and they think is a better way to do that. So, you know, the first thing that's going to happen there is we're going to apply this new streaming technology to this network analysis and monitoring stuff that they do. Now, hopefully someday, once we're there, we can then go up there. But, you know, it's just interesting to see how this stuff works out. So anyway, this is probably the most useful thing in the talk. Okay, so now let's you know, talk about where things are going here. So, you know, here's a typical batch workflow, and I don't have, this is a streaming conference, so if you didn't believe this already, if you didn't believe that there was something wrong with this, you wouldn't be here. So, but you know, the basic idea is you collect a bunch of data, you wait. Once you have enough data, you pipe it through, you extract, you transform, you load. Each one of these is a step that you have to go through the data. Oftentimes you store it, you bring in other data, and so on, okay? Then there's this other delay where you then kind of shove it over to this other part of your system, which, you know, will build an OLAP cube or do indexing or something else, run some reports. And, you know, and then at some point, you know, you finally get to actually use the data. And, you know, traditional batch windows, or maybe you do that overnight, right? Or maybe you do it once a week, okay? If you're really good at this, you know, maybe you can do this once an hour or once every half hour, okay? And, you know, by the way, this picture doesn't change if this thing, instead of being Oracle, if this thing's Hadoop, it doesn't matter. You know, it's still the same batch process, right? There's another thing that happens in this world which is really funny, which is once you've gone through this whole thing and you've collected all the data and you've stored it and you've kind of organized it the way you needed to, people run the same queries over and over again on the same data. Okay? Because what happens is, you know, you run a query and you get an answer, and then, you know, 5 hours later there's some more data, and you run that query again. And more often than not, when people run the query the second time, they run it not only over the new data, but they run it over all the old data too. I mean, I've seen it, it's just over and over again. The other thing that's going on is, in this world, there's a lot of people asking questions on this database, and they don't even know what's out there. So even if they could save the results from the previous query, they don't remember where they are, and other people can't find them either. So if you go into a place, you know, a big analytics shop, they have, you know, dozens and hundreds of replicas of the same information, right? Because everyone has there are certain questions that everybody has, and a lot of people run those individually. So you find that over and over again, people are going over the same data. So it's inefficient because you have all these delays. And it's also inefficient because the system's not set up for sharing, so you end up going over the same data over and over again. Okay, so that's kind of the fundamental problem. Now, this isn't just an old world problem, so you could be sitting, you know, I know some of the younger people in the back there are saying, yeah, you know, SQL, yeah, Oracle, this is all, you know, 20-year-old stuff. You know, I don't have this problem because I'm NoSQL, right? I don't do SQL, I'm a NoSQL person. So, you know, well, this is a picture from Twitter. So Twitter has a new thing called Storm. Storm is a real-time architecture that they've built. And the way that Storm works is you've got two paths through the system. One is you collect data, you store it up, you store it into files, you run it through Hadoop, and then you take the stuff that comes out of Hadoop and you stick it in a data warehouse, and then you know, spit out some answers. The problem with that is it takes too long, right? Twitter is a real-time service. Right, and that path can take a day. So what they've done, what Storm is this thing called the speed layer, and that's a real-time engine. And so what they do, you'll notice they split the data, they replicate the data, they send some of it to the batch process, and then they send another copy to the speed layer, so that they don't have to wait a day for their answers. okay? So this isn't about database versus NoSQL. It's not about, old versus new. It's really about, thinking about the information flows for the problem you're trying to solve. And, is it a batch problem, or is it a streaming or a real-time problem, okay? And everybody, whether they're the coolest NoSQL kids on the block, or, the oldest database people around, sort of have had this view that I've got a batch world, I've got a real-time world. And the argument that I want to make is that you don't have to do that, okay? You can build one system that does both, okay? And that's really the argument, okay? So that's kind of the setup. Are there any questions or comments, or all make sense? So, you all thought NoSQL was going to solve all this, but not yet. It will, because they're going to figure this out too, but they're not there yet. Okay. All right. So this is an old slide. It's before Hadoop caught on. But so this is I'm a little embarrassed for my field about this, but this is basically all of database systems technology boiled down into a single slide. So how do you make a database? A database is this big elephant, right? It's slow, it's plotting, it remembers everything, okay? But how do you make that thing agile? How do you make it dance? Okay, that's what 80% of the research papers in Sigma, the ones that are about real systems, that's what they're about, okay? So how do you do it? So, okay, well, there's a whole set of techniques around pre-computation. So if I know the questions I'm going to ask, which, by the way, you usually know what most of the questions people are going to ask are, because they're running reports, and you do care about how much money you're making from your advertising and so on, right? It's no surprise there. So you can pre-compute things. So there's materialized views. You can come up with nice indexing techniques for different types of data. You can cache the results of queries, and then when a new query comes in, do some sort of matching to see if you've already answered that query, right? Tons of stuff like that. Query processing with views and indexes. That's pre-computation. You can try to reduce how much I/O you have to do. So how do you do that? Well, you figure out how to keep more data in memory, right? There's a lot of excitement around that now, main memory databases. Or you organize the data differently on disk, so that if you have these wide records, but you're only interested in small portions of them, individual fields, you don't have to read the whole record, right? So you can columnar storage, okay? That's all about reducing how much I/O you do. You can try to be clever. This stuff's starting to get a little bit on the fringe, but you could try to say, hey, look, there's lots of people using my system. There are lots of people asking questions. Probably a lot of those questions have common sub-expressions, right, that I could share. I don't have to do multiple times. So I can do multi-query optimization. One thing that most database systems do now is if you've got a query that's scanning an entire relation, and another query like that comes in the old days, if you think about it, it's terrible, right? You've got a nice sequential scan going, which is what disks are good at, okay? And then another query comes in. Let's say the first one's halfway through. The other query comes in, and it starts scanning the database. Okay, and it starts at the beginning. So now all of a sudden these two things are competing, and all your beautiful sequential I/O just turned into random I/O. Okay, so what most systems do now is if there's a scan in progress and a new query comes in, it jumps on to the existing scan, and then when it gets to the end, it wraps around and gets the rest that it missed. Very, very cute stuff. Makes perfect sense. Gets you an order of magnitude or more speed up in your disk I/O, right? Maybe 2 orders of magnitude. So you can do shared processing. Then, there are things you can do to sort of make it look like it's going faster. Basically, instead of running that batch window once a day, you could run it once an hour, or you could run it once every 10 minutes, But at some point, you start, so that's called mini batch or trickle feed. And a lot of companies that talk about doing real time, that's really what they're doing, is they're kind of reducing that batch window, okay? But at some point, you're going to be limited. I mean, it's pretty well known that with the current implementations of Hadoop, anything that you want done in less than 20 minutes or a half hour, you probably don't want to do it on a regular Hadoop installation. Okay, so at some point that you start running out of steam. But those are the big techniques: pre-computation, reducing the I/O, sharing processing, reducing the batch window so you can reduce latency. Oh, and of course our favorite one, right, which is you throw more hardware at it, right? So massively parallel database systems. Okay, so I'll show you this slide again after we talk a little bit about the stream relational technology. Okay, but those are the techniques we have. All right, so what is stream processing, right? Stream processing is about real time. What does that have to do with big data analytics, right? I'm not worried about, sub-second response time. I'm worried about I'm getting, 20 terabytes of data a day, and I have to make sense of it. Okay. So what does it have to do? So this is what I want to talk to you about. Well, a lot of these, and pardon the net-centric thing, a lot of the workloads that people are being faced with now are these workloads that have some interesting properties. First of all, most of the workload you know ahead of time, right? I've got reports that I generate every day. I've got dashboards that I need to drive. Okay, I've got KPIs, right? Key performance indicators. I got metrics, right? I'm looking for some particle, and I know what that looks like, right? So most of the workload you know ahead of time. We can leverage that. The other thing is that a lot of these applications, if you think about especially a lot of the web applications that people are getting really excited about now for big data, they're not transactional in the sense of I have a small database and I keep updating it. They're these kind of additive applications where I've got this append mostly workload, right? So, the tweet stream keeps growing, and people's blog posts keep growing, and so on, right? And my click stream, people keep clicking on things, so that keeps growing. So, or my sensors are producing more data. So a lot of the applications, or a lot of things that are driving big data, right, in quotes, are not transactional, they're additive, right? So I've got more and more data coming in, and most of the time, the old data doesn't change, or if it does change, I hardly care, okay? And furthermore, I'm really interested in what happened recently, and I'm less interested in what happened in the past, okay? So you can leverage this as well, okay? A lot of these things, because you're getting very granular, very fine-grained information, you need to do aggregation, right? So there's going to be this reduction, right, that you're going to be able to do, getting masses of raw data, but you're actually outputting small amounts of kind of compiled data. So that's going to be helpful. And, there are still, as we saw when I asked the question about who speaks SQL in the audience, SQL is still one of the main ways that people process data. I always like to say, what's the most popular language that NoSQL people use for doing data analytics? Any guesses? SQL, right? They run Hive, right? Maybe they run this thing called Pig, which was done by a guy who got his PhD in databases and isn't exactly SQL, right? But that's what they use, right? And there's a reason for that. It was built for that sort of thing. Okay, so these are all things that are working in our favor. Okay, so remember this picture, right? This is this marketing picture where, I got months out here, I got real time out here. So the argument I want to make, and the argument I have made, is that what you really want is this whole spectrum, right? There's a bunch of things that you're going to be doing, absolutely, looking over historical data, right? You're collecting data over days and weeks and months, and you absolutely want to determine trends. You want to look and see, how's the business doing over, this year compared to last year. That stuff's absolutely important. In the meantime, there's a bunch of things that we have to do where if we're doing interactive processing, we don't want to wait hours. Maybe we'll wait minutes, but even that we don't really want to do. So seconds. Or if we're trying to sort of customize, if we're trying to figure out what ads to show somebody, or we're trying to figure out, whether I should, turn this valve on or off in my processing plant, that's got to be out here. That's got to be, in sub-second land. Okay, so the argument is you need all these time scales. And so if you need to go from really, really slow to really, really fast, you sort of got two ways you can do it, right? One is you can start down here, right, which is making the elephant dance. You can say, okay, I've got a system that was designed for batch processing that gives me answers, on the scale of hours or days, right? And I can try to figure out how to be smart and push it up this hill. Or you could do what I think you should do, which is start with a system that gives you instantaneous answers, and then if you have to, you can slow it down, So, when I talk to people about this stuff, I'm like, people are like, yeah, I don't really need real-time data. I only, need updates like once an hour. I'm like, okay, it's going to be hard, but I can slow my system down if you want, And so the argument is, if you want to build something that if you don't want to do that Twitter thing where I've got, one path for batch, I've got one path for real-time. If you wanted to build a system that could do both, I argue you should start from the fast side and make it slower rather than go from the slow side and make it faster. Okay, so it's just kind of a cute picture. All right, So here's the thing that a lot of people get wrong with stream query processing. They think that I've got data streaming in, right? And I'm going to run it through my query processor, my continuous query processor, okay? And because this data is coming in continuously, I got to get those answers out continuously, right? So this is a picture. This is a sad picture. This is when they were trying to cap the well, in the Gulf of Mexico when the BP oil spill happened, right? And they kept trying to cap this well, and this data is coming up, and the oil's coming up, and they can't cap it, right? That's what everybody thinks stream processing is, okay? And the problem with that is most applications don't want streaming answers. They've got streaming data, but they don't want streaming answers because they're not built that way, okay? So the argument is, why build a stream processor? Well, because all the data in every database in the world started off as a stream, right? It was created somewhere, it went through the network, it ended up in the database, and that keeps happening, and that's why databases grow. Okay, so all data is streaming data. Okay, so if you could build a stream processor, the amount of data you could use it on is everything, roughly speaking. Okay? Oh, sorry, I tried to remove all the marketing stuff. So that's great. As data's coming in, I want to process it. I don't want to store it to disk and then pull it back out and run the query on the data that I just ran it on. Every time a new record comes in, I want to take that record and I want to update all the answers to all the queries that I know I'm trying to answer. Do the minimum amount of work I need to do to update all those answers, right? Because that's going to be much, much cheaper than trying to do it all later, okay? So for efficiency, you want to process these streams as they're coming in. But the trick is the answers that are coming out of this thing, right? So that's alerts, so some things, I'm sorry, I jumped ahead. So the answers that come out of these things, you should let sort of the usage drive when those answers come out, okay? So if you're doing things like alerts or triggers or real-time dashboards, absolutely, that should be real-time, it should flow right through, okay? And data comes in and answers should be coming out, okay? But if what you're doing is generating reports once a day, that's fine. You should be able to, have that report being created while the data is coming in, and then when you say, hey, I'd like to see my report, it should be ready for you, okay? So you shouldn't have to have data being forced at you all the time, because that's not the way most business processes work. That's not the way most people work, okay? They want to get the data when they want it. They don't want it forced at them, okay? But you can build a system that does that. That's the argument. Okay, sorry. So here's the way we want to build that system. So you've got data, I'm sorry, let me see that. So here's the way we want to build the system. We've got a bunch of data coming in, and what we did is we took an existing database system, we took PostgreSQL, and we added to it, so we kept all the great stuff that PostgreSQL had, which is SQL, user-defined functions, the storage and indexing and so on. And then we added into it the stream processing engine, so this thing that's capable of, okay. Really? Oh, okay.
That's your question.
Oh, okay, sure. Gotcha. You scared me. Okay, so we put in the stream query processor, okay? And then here's the fun part, is given that you've got a system that's got a stream query processor and a traditional tabular processor in it, what you can do is this kind of thing. You can say, okay, as data comes into the system, I'm gonna write it out to the database. So it's just like normal. Data comes in and you kind of load it into the database. Okay. In addition, I can sort of tee it, run it through. It's kind of a micro version of that picture I showed you from Twitter, but it's all in one system. I run a version of it through the real-time stuff. And then the beautiful part of that is, as I'm computing my answers on the fly, you remember that query I showed you with the windows, right? I'm computing those queries. I can do two things. One is I can output the answers right away. So if you're driving, alerts or a real-time dashboard, you can do that. But more interestingly, I can take those things, I can write them back into the database. Okay? So I don't have to give them out right away. I can just basically be doing that pre-computation trick, putting stuff in the database. And then what's beautiful about that is two things. One is, if you want to get answers to streaming queries, you don't need to know streaming. You can just write a SQL query against these tables, and it'll work just the way nothing's changed. Your world hasn't changed at all, except that your system just got much faster. Because it doesn't have to go out and run that query, it's already got the answer stored. Okay? The second thing that's nice about it is if I've got a lot, if you think about it, a lot of my streaming queries aren't, compute this average over It's not just, tell me the average over the last minute. It's tell me the average over the last minute and tell me how that compares to the average over the previous minute, or the average to that minute yesterday, that same exact minute yesterday. So you need historical data. So you can start doing joins between the data that's coming in new and the data that you got already, okay, because it's all stored in that database. So that's the architecture. And we had a paper in CITER 09 that sort of went into this argument that I just made for you, okay? So, so how does that look? All right, well, what we did is there's no way, okay, that's fine, okay. So, how does that look? This is our language, there's lots of ways to do it, and this is actually an old version of the language we came up with. But we have a command called create stream. It looks just like create table. You give it a name. The only difference is you have to identify one of the fields as the thing that you're going to use as time, okay? Because time is, in a streaming system, time is kind of what drives things, okay? So, so we have two types of timestamps, and this is also really important. I'm not going to, unfortunately, get to this part of the talk, I think. You can say, hey, data is coming in from devices, and it already has a timestamp on it, and that's the timestamp I want you to use, right? Or you can say, timestamp this thing as of when it shows up at my server. Okay, so you can either do user timestamps, which means the timestamp's already in the record, or you can do what we call a system timestamp, which says we stamp it as it comes in. Now, it's going to turn out that stamping things as it comes in is much, much easier, right? Because you're guaranteed that everything's in order. Okay, that we love that. Unfortunately, nobody wants to do it. Okay, we try to get people to do it. Nobody wants to do it. Everybody wants to use a timestamp that's in their original data because that's when things happen. Okay, and that causes all sorts of complications, which we'll have to talk about over coffee. So that's the technical part of what I want to talk about. Okay, once you've defined this thing called a stream, I already showed you how to do this. You can use it in a query, and the rule is you can, in your queries, the from clause, you can put streams, you can put tables, you can put combinations of streams and tables. When you use a stream, you got to put a window clause. Because remember, that's how we know what this query means. The window tells us, look at this much data, and give me a new table, every in this case every 1 minute, right? Once we've done that, what we've got is a sequence of tables, and we can run the rest of our Siebel over. Okay, so that's cool. You can do some nice things, like you could say, okay, because see, now we get to leverage the power of the language, so we can create streaming views. So here's a stream that's basically the result of a streaming query. Okay, so it's a virtual stream. It's a stream view. Okay, and I can write queries against this just like I write queries against my raw stream. Okay, and then if you remember, the other thing I talked about is you can take answers from the stream processor and stick them in the database. Okay, so how do you do that? This is old syntax, but basically you can say, okay, I'm going to create a table. All right, this is just vanilla SQL, create a table. And then we have this concept called a channel that basically says, take this stream and stick it in that table. So as long as they're schema compatible, that's just gonna take this table and use it as an archive of the answers that are being spit out every time a window closes in this stream. Okay, and that's how you do it. And once you've done this thing is just a table. If you run, our system's based on PostgreSQL. If you take your favorite PostgreSQL query and run it, it'll run against this table. There's absolutely nothing special about this table. So that's kind of nice. Now, once you've got this together, now you can start doing things like this, where you can say, okay, I want to do a join between my stream and what it looks like now versus the archive of that stream. In this case, this is kind of ugly Postgres syntax, but saying, every time a window closes, join it with that same window from the same time a week ago. Okay, and then tell me the difference. Okay, and you can see it's all just using that same language. So basically, what we've done, that's a stream, that's a table. Okay, okay. And all right, I'm going to skip this. The other thing I'll just mention briefly, I won't really skip it because it was Celestia's PhD thesis. Once you've so if you think about it, we've moved from a world where we're collecting data and we're waiting for queries, we're kind of helplessly waiting for queries to show up, into a world where we've got queries and we're basically running them as the data's coming in. Now, if you think about that, there's a really interesting opportunity there. which is I've got a set of queries I'm trying to run. I've got 100 or 200 or 1,000 queries I'm trying to run. If you're smart about it, you can look at those queries and figure out where do those queries overlap, okay? So sure, if I got one query, I can put it in the system, and then as data comes in, I'll run data through the query. But now as new queries can come in, I can look at them and I say, hey, how much of this work am I already doing? And then rather than doing it again, which is what you do in a traditional system, you can just kind of bolt on, you know, the new parts of the query to the kind of the intermediate results that you're already computing. So you get this tremendous reuse, right? You get that sharing thing that's an important way of making things run faster. Okay? So this is a big part of it too. Okay, talk just briefly about performance. This is a little hard to read. I actually haven't looked at it for a while. So this was a workload where we had 720 million records. Okay? And we said, all right, what if you take all those, what if you save up a whole batch of 720 million and you run it, okay? So that takes a day and you get a certain performance. Or you could split it into 3 batches. Now each one is 8 hours and you can run that. Or you can split it into 6 batches. Now each one is 4 hours and so on down to, I forget how many batches, I don't know, you have to do the math, but every half hour or 15 minutes or something, okay? And what this graph is showing is the amount of data you can basically run through the system per day, right? So as you go this way, your latency, you're getting lower latency, okay? So you're getting answers more often, okay? As you go this way, you're pushing more data through the system. So in a traditional system, you have a trade-off. You could say, okay, I can maximize my throughput, right? This is Hadoop with 8 nodes, 60 nodes, 32 nodes. Okay, or 4, it doesn't matter. But, I can, if I'm willing to wait a day, I can batch everything up and then I can let Hadoop do what it does best, which is take a big chunk of data and churn through it. All right, and I can get a certain throughput per node. All right, but if I can't wait a day, if I have to go faster, then I've got to turn the crank on Hadoop much more often, and I can do that, but then my throughput is going to go way down. The amount of data I can actually push through the system is going to go way down, which means I'm going to have to buy much more hardware, which is why you have a lot of Hadoop systems out there that, are going to have to scale to thousands of nodes to be able to do anything useful. Okay? With the continuous system, that trade-off goes away. In fact, it's a little crazy. Actually, the throughput goes up as you make the latency, as you get answers more often, right? So as you decrease latency, throughput goes up in this particular query. It's very weird, right? So we would have been happy if it stayed the same. In this particular case, it's interesting. The reason why it goes up is because this was a big aggregation query where we were looking for like hundreds of millions of users, aggregating data about them. And it turns out that you see more users in a day than you do in 15 minutes. And so it was actually cheaper to run it every 15 minutes than to run it over the whole day. Okay, but in some sense that doesn't matter. What really matters is, in a traditional system you have to choose between high throughput and low latency. In one of these continuous analytics systems, that trade-off goes away. You can just run it at full speed all the time. So it's very cool. All right, so good. So let me try to get to the conclusion here. And I'm only going to get through argument 1. I have argument 2. That'll have to stay for another talk. So, okay, remember we did the elephant dancing lessons, right? What are the things that we do to make database systems go faster? All right, well, we reduce how much I/O we have to do, right? We do shared processing, right? We look for common sub-expressions or common scans. We try to shorten the batch window to get lower latency. We try to pre-compute things ahead of time so that when we ask the question, we already know the answer. And we throw hardware at it, right? Those are our 5 weapons to make things run faster. All right, well, think about the system we just described. Okay. This continuous processing, if you process the data as it's coming in, you don't touch the disk. The disk is at the end. It's not in the beginning. Okay? So we've done I/O reduction. In fact, we've gotten rid of I/O. Okay, so did that one. Shared processing, I told you how we do that. You have all the queries, so you can analyze them and figure out which parts are shared and then only do those once. Right? And that's something that's easier to do in a shared system because you have all the queries. In a traditional system, even though you see the same queries over and over again, the system doesn't take advantage of that. It reacts to every query as it comes in. Okay, so we've done that. And then latency reduction, our computation tick is every record. Okay, so that's as low as it's going to go. Okay, so we've done that trick too. So just by building the system the way we've done it, we've already done the top 3 out of the 5 things that you do to make a database system go faster. It's very cool. If you put it together with the persistent store, like I was showing you, where we built the system that has a streaming engine and the persistent engine, right, and the tables, well, that does number 4, right? Because as that data is streaming in, you run it through your queries, you take the results of those queries and you store them in the tables. So then when somebody wants the answer to that query, they do a lookup in the table, it's just one lookup and they get the answer. So that's how you do pre-computation. And for the hardware vendors in the audience, which I don't think there are any, there's still good news, you can still throw hardware at it, right? It still parallelizes. So, every system is going to have a limit to, how much data you can get through a single node. So you're going to have to extend this to other nodes. Now, if I wasn't being threatened with bodily harm to stop talking, what I would do next, and I don't have time, is tell you about a little bit about a couple cool things that it turns out you have to do. One is, because data doesn't come in order, you have to figure out how to build a system that is stream-based, it's order-based, but can tolerate data being out of order. And the short answer to how you do that is you treat it as a data parallel computation. So data will tend to come in chunks. So when you see a chunk that's in order, you process it. If something comes in that's not in the current order that you're working on, you basically fork off a parallel job, okay? And you sort of compute that one on the side. And you can keep doing that. And then what's beautiful about doing this in the SQL environment is you can create a view. You can write a view over the top of all those different pieces that basically pulls them all together before it gives you an answer. Okay, so what we're doing is, as data is coming in, we're forking off jobs that are running concurrently in real time, but are actually running at different spots in data time. But then we give you a view mechanism so that when you ask your question, you see all the data that you should have gotten. Once you've done that, that also makes the system parallel, okay? That was the second part of the talk. And then the last part of the talk is I was going to say thank you very much, and are there any questions? So thank you very much. Are there any questions?
We have time for a few questions.
At the very beginning, you said how the streaming relational approach was invented in anticipation of the flood of data. Now, 10 years later, the flood's starting to come, and I imagine that with the availability of huge amounts of data, there will be new applications forced on people. Do you think that the streaming relational approach is, how well do you think the streaming relational approach will be able to handle these new applications? Do you think it'll change? Do you think the Solver approach is stimulating?
Yeah, so I do think that the time for this stuff is definitely closer than it was when we started. And we are seeing a lot of cases where this kind of technology can be useful. I think this concept of, I'm going to back off a little bit from stream relational because it carries all this relational baggage with it. But I think what is going to happen is people are going to realize, just like the database people did 10 years ago, that just because data is moving doesn't mean that it's different than data that you've stored, and that you should be able to build this kind of unified system. So maybe it's a database system that's doing this kind of pre-computation, and if you look at how people use database systems in these environments, that's kind of the only way they survive, is they do this stuff by hand. So it's already sort of starting to happen. But the reason I backpedal a little bit is it doesn't have to be a SQL system, right? You could do this with Hadoop. Right, you could build a streaming processing system that's tied very tightly with a persistent system. And in fact, in the AMP lab, which is this new project that we're running over in the CS department, we're building such a system. We built a parallel computation framework called Spark, which is it's a competitor to Hadoop that's meant for handling machine learning. So it's really good at doing iteration over data. And then we're building a streaming version of that, and it's actually they're going to be the same system. So long answer to your question, but I think the short answer is that, yeah, I think this is going to be the only way that systems are going to be able to keep up with the amount of data we're seeing. And whether it's going to be buried in a SQL system or buried in some NoSQL system, I think it'll be all of those.
So Mike, you just mentioned about the indexing, right? The streaming indexing of the query rather than just keep.
I'm sorry?
So let's think about that like a Google. People start doing their query, the question, like they have 100,000 type of the word that you can index everything else. But once you do the query is just not only about the indexing, but it's also about the ranking there. If you do stream ranking while you're doing
Oh,
indexing,
well, you came in late, right?
yeah.
Okay.
No, then I then the answer is off.
I did show kind of how that worked. You know, you learn this trick as a professor. And no one else is going to tell them that I didn't really actually say the answer.
Yeah, the answer is obvious.
In a traditional database, if I do a query and then wait 10 minutes before iterating over the result, I get what was in the database 10 minutes ago. In your system, if I do that query and then wait 10 minutes before iterating over it, what's the starting time and is there an ending time of the results that I'm streaming over?
Yeah, so good. So this is a good question. So there's two ways it works. One is that there's this continuous query that's running, and you can just kind of latch onto that, and then you will get, the guarantee we make you is that you will get an answer based on every single record that has arrived from the beginning of time, even if it arrived out of order. So if you latch onto a streaming query, you'll get, if you wait 10 minutes, you'll get that new 10 minutes of data too.
And
but
it continues into the future.
And it continues into the future. And you can also tell it when you want to start. We have a clause that says start, which only works, by the way, if you already knew that query was coming. Right? So, but the other thing you can do is if you're storing the results of the streaming query into a table, the way I was talking about, then you could just run it and you can say, I'm interested in this time window. And then you can get whatever time window you want. So it gives you that flexibility.
One more quick question.
So it seems like the results will work only for the metrics which can be aggregated. Like if, let us say, there are unique property for each log or each request, then it will do probably a full index, full table index kind of thing or something. Full table scale.
Right. So I guess Muthu must have left, right? But Muthu gave a talk here a day or two ago. Where he, I'm sure, well, I don't know because I didn't see his talk, but he and people in his community have done a really good job of understanding which things you can do in this like very incremental mode, and which things are holistic, where you need all the data. And absolutely, there are queries you could ask that you could run into memory problems because you'd have to keep all the data over all time in your window. And for those, there are these kind of approximation types of algorithms, these things that I assume Muthu talked about during his talk. By and large, most of what people want to do that we found does fit into this framework. And even very granular aggregations, like if you've got 200 million users and you're trying to track them, you can do that. You just have to be smart about the data structures you use. So it's another part of the system that I didn't talk about. We have what we call a high cardinality module, which basically uses compressed bitmaps and things to keep track of large data spaces that are sparse. But absolutely, in the limit, there's ways to get into trouble.
Great. Let's thank the speaker again.
Programming interface for wireless sensor networks, and that was a very popular system that we built. And then a little after that, we built this thing called Hi-Fi, which this is a picture of, which basically combine these things. So we use TinyDB out on the edge of the network to manage collection of data from physical devices. And then we use a streaming engine, Telegraph CQ, to basically aggregate data and build a hierarchy. So you'd have a bunch of edge devices. You'd have a bunch of things out measuring, sensors and so on. Those would connect to sort of gateway devices, and then there'd be a hierarchy of gateway devices and servers up until you got to maybe headquarters where you had your big data warehouse. And our view was you'd use SQL out here because we did that with TinyDB. You'd use SQL in the middle here because that's what we could do with Telegraph CPU. And then you'd have your traditional tools and BI tools and stuff up here. Okay. And what this is a picture of, we built this thing called the loudmouth sensor, and we demonstrated it at the LDB conference. So everyone that came in got an RFID tag that they wore on a lanyard. And then we had, around the conference room, we had stations set up where we had an RFID reader and then a little network of wireless sensor modes that had microphones on them. And at each station would measure the total noise volume and would count the number of people in the neighborhood, and then would divide. And we built a SQL view on top of that that basically was loudmouth sensor. And what it would do is it would give you the ratio of noise to people, and then we'd just run a SQL query over that to figure out where are the loudest people in the room. And then we had loud people kind of go from one place to another and make a lot of noise, and we showed how we could track them in real time. But the important part of that was you didn't have to write any imperative code. It was all done with views and queries, which was something that a lot of people working on sensors at the time, thought hadn't really thought you could do it, or really hadn't thought about doing it. Okay, so that's sort of the genesis. That's kind of the sort of the research milieu, if you would, of a lot of the streaming database work that was done, sort of 10, 12 years ago. So, the story I have, so a couple of years after we use it, we write SQL on it, okay? So it's a really nice it's a nice, simple way of being able to move, 30 years of data analysis technology, into this new world of moving data, okay? And, this wasn't just our idea. I mentioned the MIT Brown guys. A lot of the really good work on understanding exactly what these operators should do and what they mean was done by Jennifer Whittam and her group at Stanford. And actually, I have a slide on this. It was a big topic in academia. Okay, so every time that window closes, you can conceptually think of a new table coming out. Okay, and then our particular semantics were that the results every time you produce a new result, it sort of gets appended to what you had already. There's other ways to think about it, but that one turns out to be pretty simple. Okay, so here's an example. Let's say that you were doing an advertising thing, and here's your query. So every 3 seconds, give me the revenue for pay-per-click ads per advertiser over the last 5 seconds, okay? And the way you do that in a system like the one we built is you write a SQL query. Instead of having a table in the front clause, you put a stream there. Okay, so this is an impression stream. And what I'm doing is I'm looking at this impression stream. I'm only interested in ad impressions that are of this type CPM. That's advertising lingo for pay-per-click. It's cost per 1,000 impressions. CPM. And I want to group those by the advertiser, and for each one I want to output the advertiser and this metric that tells me how much money I made from it. Okay, so that looks almost exactly like an SQL query, except that this thing's not a table, it's a stream. And so in order to turn it into something that we can understand, we use this window clause, which is this thing here. And the window clause just follows what we're saying here. It's got 2 pieces. It says visible 5 seconds. So it says, I want to look at, when I produce my table, I want 5 seconds of data, right? So take the last 5 seconds of data, and do that every 3 seconds. That's what advanced. Wrapped up the Telegraph CQ project. One of my PhD students was graduating. We got approached by, by some investors who were interested in real time. Michael Stonebreaker, who had a project at MIT that he did with some folks at Brown, had spun out this thing called Streambase. And people, as investors tend to do, say, hey, we should do that. And so one thing led to another, and we ended up starting this company called Treviso. And we ended up in kind of a very different place than the picture I just showed you. And we ended up there, because we went out into the world. When we started, our view was we were going to go out and be the kind of the analytics for the Internet of Things. But that's sort of not the way it turned out. At least it's not the way it's turned out yet. And so, we ended up kind of getting involved in sort of the big data analytics world. And as was mentioned in the introduction, last week the company was acquired by Cisco, which is actually one of our first customers. Another early customer was UPS, the package delivery guys, and so it's people like that were interested in the technology, but none of these people were deploying those little sensor devices, right? It was all sort of big stuff on the network. Okay, so this is kind of the experience I'm going to be talking about. So here's a little background. Maybe some of you already know this, but think about a stream as a sequence of records that's unbounded, right? Just keeps coming in. All right, we all know what a table is. A table is a set of records, right? So, got rows and columns. And we all know how to get information out of tables. We write SQL. Okay, so SQL queries apply to tables. And then, so the only thing you need to do to bridge from this world of continuously arriving data to the old world that we all knew and understood, which was the world of tables, is use this thing called a window operator, right? Which is just a single query operator that converts this continuous stream into a sequence of tables. Okay, so here's a bunch of records coming in on the stream. Here's our window operator that we'll talk about in a little bit, and what pops out of that is a table. Okay, so every time the window operator spits something out, what it spits out is a table. Since it's a table, we already know how to do the right answer either. And my argument that I want to make to you is what you really need is a system. Hey, Ron, you want to build a system that combines kind of the best, I'd like to say the best of a traditional store first system plus a streaming system. And I kind of use the clunky term stream relational for that. Okay. And so that's really the technical part of the talk. And then, this is kind of an interesting checkpoint for me, as was just mentioned. There was a bunch of research. There was a company. The company just got bought. So, along the way, I'll sort of maybe give some insights or reflections on sort of what this process has been like and what I learned along the way, both technically and maybe a little bit about why it's a good thing I have a tenured faculty job. Compared to why I'm not in business, I guess I should say. All right, so that's it. So let's start. So, around the turn of the century, a lot of us got excited about, the Internet of Things. Everything was going to be connected. Everything was going to be collecting data, pumping that data out. And, how were you going to make sense of this data? You certainly weren't going to stick all that data into Oracle and then try to run queries on it. That didn't seem right. So there were a bunch of people around the research community, especially the database research community, saying, how do we build technology to do the kinds of things we like to do with data, but do it in this world where everything's connected, data is constantly on the move, okay? So that was, 10 years ago. At Berkeley, we spun off a bunch of, kind of a series of research projects that were aimed at that basic idea. We had a system called Telegraph CQ, which was one of the early database streaming systems. I'll talk a little bit about that. It's actually the sort of the foundational work that led to the system I am going to talk about. We built a system called TinyDB where there was a burst of energy here at Berkeley on these little, I'm going like this because these little wireless sensor modes that you could build ad hoc networks of, and they would be able to sense environmental readings and collect them and route them to this ad hoc network. So we did this work on TinyDB where we basically made SQL the program.
Welcome to the last day of the conference. Thanks for all of you who have shaken off the food and wine hangover from last night to this morning. Today we'll have a session on streaming and analytics frameworks. And our first speaker, we're happy to have Michael Franklin. He's a professor of computer science at UC Berkeley. He's the director of the Algorithms, Machines, and People Lab, and the founder of Treviso, which last week was bought by Cisco. So, congratulations.
All right, thank you.
And his talk will be on continuous analytics.
All right, well, thanks. I don't know. I know you guys have had a wide range of talks on a wide range of different topics. I don't know how much database stuff you've heard so far, but how many people in the audience speak SQL? Oh, okay, so good. All right, I'm going to be in trouble, actually. All right, okay, so why don't we just jump into it? So yeah, continuous analytics. So here's the overview of the talk. The argument I want to make to you, and maybe you don't have that much invested in this, so maybe it'll be okay, is that sort of the traditional way we think about doing analytics, whether it's a database or a NoSQL, Hadoop-based system or whatever. We like to take a bunch of data, we store it, and then we turn around and we pull it back out and we try to analyze it, okay? And if you at all think like an engineer, you have to realize that seems kind of inherently wrong, right? At least for certain use cases. And so, you know, the argument I want to make is if you think about sort of big data problems in general, you've got this streaming amount of data just constantly coming in, and that's not what you want to do. What you want to do is you want to be able to process that data as much as possible as it's arriving. Okay, because, and we'll go into this, but you know, obviously, writing it out to disk and bringing it back is expensive. You know, going through all the, even if you're not writing it to disk, going just through that whole software stack all the way to store the data and then bring it back is expensive. And so, you know, to the extent you're able to do it as data is coming in, you'd like to process it. Okay, and so that led to a class of systems called streaming systems, but they're not exactly